Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Smart Grids. Lecture prepared by engineer Jesus Velasquez Bermudez, Ph.D. Distributed Generation. In 2014, IBM estimated that companies in the energy and utilities sector, which used big data and analytics, reported 23 times higher productivity than those that did not. Distributed generation, DG, is a small-scale generation technology that provides electrical power closer to customers than power plants. DG offers a multitude of services to utilities and consumers, including standby generation, peak shutdown capacity, and base generation. DG investments improve on-site efficiency and bring environmental benefits, especially in combined heat and power applications. A multitude of events have created a new environment for electrical infrastructure. A key element is to build and operate several DG units near the load centers instead of expanding power plants located far from customers. DG can improve the efficiency, reliability, and operational benefits of the distribution system. A distributed power unit can be connected directly to a utilities consumer, transmission or distribution system, to provide services at peak times. Distributed generation technologies. The term distributed generation, DG, refers to the production of electricity near the consumption place. The main technologies used for distributed generation and the optimization of a system that contains these technologies are presented. The term distributed generation refers to the production of electricity near the consumption place. The distributed generation resources are renewable energies and cogeneration, simultaneous production of heat and electricity. Renewable energy is energy from natural resources such as wind, sunlight, tides, waves, geothermal heat and biomass. The optimization aims to minimize the electricity production costs, ensuring that the load is served reliably. Distributed generation, DG, also known as distributed energy, on-site generation, or decentralized energy, is the generation and storage of electricity using a variety of small devices connected to smart grids, known as distributed energy resources, DER. Conventional power plants, such as coal, gas, and nuclear plants, as well as hydroelectric dams and large-scale solar power plants, are centralized and often require electrical power to be transmitted over long distances. Instead, DER systems are decentralized, modular, and more flexible technologies that sit close to the load they serve, albeit with capacities of only 10 megawatts, MW, or less. These systems can be composed of multiple generation and storage components. In this case, they are called hybrid energy systems. DER systems typically use renewable energy sources, including small hydropower, biomass, biogas, solar, wind and geothermal, and are increasingly playing an important role in the electricity distribution system. A device for electricity storage can also be classified as a DER system and is often referred to as a distributed energy storage system, DESS. DER systems can be managed and coordinated within a smart grid. Distributed generation and storage enable the harvesting of energy from many sources and can reduce environmental impacts and improve security of supply. The table shows the most used distributed generation, DG, technologies and their typical module size. Below are some of the DGs with their simple conversion formulas. Hydropower systems use the energy in flowing water to produce electricity or mechanical energy. For run-of-the-river micro-hydropower systems, a portion of a river's water is diverted to a water conveyance, channel, pipeline, or pressurized pipeline, penstock, that delivers it to a turbine or water wheel. The moving water rotates the wheel or turbine, which spins a shaft. The motion of the shaft can be used for mechanical processes, such as pumping water, or it can be used to power an alternator or generator to generate electricity. The wind turbine works in the following way: the wind kinetic energy is transmitted to the blades, which drives a shaft coupled to an electric generator that converts, the wind power into electric energy. The main parts of a wind turbine are rotor, blades, tower, and nacelle that contains all major components such as shaft, gearbox and the electric generator. The term photovoltaic comes from Greek, which means light, photo, and electricity, voltaic. A photovoltaic panel transforms sunlight directly into electrical energy. The main components of a photovoltaic panel are solar cells, which consist of two or more layers of semiconductor material, the most common being silicon. When the silicon layer is exposed to light, the electrons in the material are agitated and an electric current is generated. The current generated by a single cell is small, but the series and parallel combinations of these cells can produce currents high enough to be used in the real world. Depending on the nature of the semiconductor material, there are three different types of photovoltaic cells: monocrystalline, polycrystalline and amorphous. Optimization aims to minimize electricity production costs, ensuring that the load is reliably covered. The optimization is done with the mathematical model shown in the text. In the figure there are three types of generators: hydroelectric, G1 having 72 megawatts, thermoelectric, G2 having 50 megawatts, and a wind turbine, having 1 megawatt. There is also a 100 megawatts consumer, C1. The cost of generated power is given by the Romanian Energy Regulatory Authority. The table presents the average prices for different types of energies. The calculation is performed by selecting in NEPLAN the optimal power flow analysis. The results are 0.702 megawatts active power losses and a generation cost of 504 lei/h. Also, the results shows that most of the power is supplied by the hydro generator. The other producers must lower the prices of power delivered to have a greater importance in the system. Microgrids are advancing in terms of intelligence, distribution, and flexibility. Power grids are dominated by cutting-edge power electronics and artificial intelligence techniques, and this trend could continue for many years to come. Distributed generation in power systems, an overview and key issues. The need for smart electricity systems with minimal technical losses and minimal environmental impact is driving the option of distributed generation, DG, which can offer several advantages, such as reduced transmission and distribution system resources, increased reliability, better power quality, etc. In recent years, DG has become an efficient and clean alternative to traditional sources of electrical power, and recent technologies are making DGs economically viable. Today, DGs are part of distributed energy resources, DER, which include energy storage and response loads. The main driving forces behind DG penetration can be categorized into environmental, business, and regulatory factors. There are several small generators that produce very small or no greenhouse gas emissions. The need for smart electricity systems with minimal technical losses and environmental impact is driving the option of distributed generation, DG, which can offer several other advantages, such as reduced transmission and distribution system resources, increased reliability, better power quality, etc. Report submitted in March 2008. Case study. The Government of India has taken several measures, including tax and financial incentives, preferential rates for the promotion and proper use of renewable energy systems/devices in the country. Significant achievements have been made, with the creation of more than 13,700 megawatts of grid interactive renewable generation capacity, representing approximately 9% of the country's total installed capacity. Of these, 6,795 megawatts of capacity were added during the 10th plan, carried out between 2002 and 2007, against the target of 3,075 megawatts. In addition, more than 5.5 million decentralized off-grid renewable energy systems or devices, mainly biogas plants and solar photovoltaic lighting systems, have been deployed to cover basic cooking and lighting needs in rural homes. In the table, technologies 10 to 18 can be considered as renewable DGs. The other technologies could also be referred to as renewable DGs if they are operated with biofuels. Similarly, to the centralized generation, the following three generation technologies are normally used for distributed generation: synchronous generator, asynchronous generator, and power electronic converter interface. The Electric Power Research Institute, EPRI, predicted by 2010, that 25% of newly installed generation will be DGs, and a similar study by the Natural Gas Foundation puts the share of DGs in new generation at 30%. Table shows the various methods used for DGs location and integration in the power systems. There are difficulties in the exploration of renewable energy sources in the country. The main constraints they face are the inherent and intermittent nature of renewable energy sources, leading to low capacity utilization factors ranging from 17% to 70%, depending on the resource, and grid location and synchronization limitations. The relatively higher capital investment compared to conventional energy projects, and the requirement of preferential tariffs, in addition to other fiscal and/or financial concessions, are necessary to make investment in renewable energy a commercially attractive proposition. The table presents several DG options in India. The table shows the wind power potential and power generated till March 2008. India ranks fifth among the world's wind energy producing countries, after Germany, Spain, the United States and China. The estimated potential is about 45,000 megawatts at 50 meters above ground level. Wind farms have been installed in more than 9 states. More than 95% of the installed capacity belongs to the private sector in 7 states. A good number of wind turbine manufacturers are active in India and produce wind turbines with power outputs ranging from 225 kilowatts to 2,100 kilowatts. Many water pumping windmills and small wind turbines have been installed in the country. Hybrid wind solar and wind diesel systems have also been installed in some locations. The table shows the equivalent saving of coal and other pollutants by use of wind power generation. Renewable energy is the answer to climate change and global warming. This carbon-free energy is considered the energy of the future whose development and deployment requires all possible stimuli. It has played a central role in all international deliberations on the future of the planet in the context of global warming. Table shows the potential and installed capacity of renewable energy sources, RES, till March 2005 in India. India has tapped into a very small fraction of the renewable energy sources available. However, the government is promoting the RES with different policies. India has experienced rapid annual growth in installed renewable energy capacity between 2012 to 2013 and 2018 to 19. The compound annual growth rate of renewable installed capacity in the same period has been 18.80%, representing an impressive 2.8-fold increase in renewable installed capacity. Optimal location. There are several methods available for optimal placement of DGs for different purposes. Based on the priorities of the objectives, a hierarchical analytical process is used to suggest the best location of the DGs. The suggested methods are good enough for the current state of the electricity system, which is constantly changing for various reasons such as grid expansion, load concentration, structural and regulatory changes, etc. The optimal location may not be optimal after years. In addition, with the increased level of DG penetration, the optimal locations continue to change, and a new coordinated replanning study is required. The future availability of a fuel supply system will also affect the optimal location of DGs. Electrical modeling issues. When the penetration level exceeds a certain threshold, it will no longer be appropriate to model static loads characterized by the amount of active and reactive power consumed. The importance of modeling new DG technologies has already been recognized in the development of dynamic models of fuel cell systems, microturbines, dual-feed induction machines, and generic loads has been reported. Depending on the dynamic phenomena, various models can be used in analyses and simulations. For the study of dynamic or transient stability, it is extremely important to have models that reflect the main dynamic characteristics of the system with reasonable accuracy. This implies that DG owners must make all relevant DG technical characteristics available. Here, not only the static characteristics of the DG units are important, but also the characteristics of the main controls, such as the regulator, voltage regulator and excitation system of a synchronous generator, etc. Role in new market regime. DG does not only displace the energy produced by central generation but also the associated flexibility and capacity. DGs play a vital role in electricity markets emerging around the world. Depending on the structure of the market where they are installed, DGs can participate in energy markets, daily in advance, 1 hour in advance or in real time, and can be used to provide ancillary services in order to improve the economic viability of some DG projects. DGs must face several technical, regulatory and policy constraints. Demand response effect. The electricity market exists in several countries and demand response is encouraged to improve the economics of the electricity market and customers. This demand response may not be very beneficial for DGs, as they could lose revenue due to its impact. Voltage control in distributed generation. Voltage control in distribution networks with distributed generation. In recent decades, there have been significant changes in the electricity generation sector. Growing environmental awareness, higher fuel prices, and the goal of reducing energy dependence on fossil fuels have driven the development of regulations to promote efficient technologies, such as cogeneration and renewable generation. Among the main challenges that distribution system operators must face for the proper integration of distributed generation, the focus is on voltage control and analyzes technical aspects in high, medium and low voltage networks. The work is the result of the REDS 2025 project, funded by the European Regional Development Fund, ERDF. Real and representative distribution networks are analyzed, which includes a high voltage network, 5 medium voltage networks and 4 low voltage networks, which include different segmentations. The networks considered are: one high voltage network is a 45 kV ring made up of 11 substations, and in which 4 distributed generators are located with a total power of 45 MW. The single line diagram, SLD, is in the graph. 5 medium voltage networks, MV, from 11 transformer stations, 5 km, 7 MVAs of purely underground transformer power in the urban network, to 48 transformer stations, 50 km, and 11 MVA of power with 94% of the overhead network, in the mixed segmentation. 4 low voltage networks, V, associated with transformer stations from 250 kV, totally overhead and long sections, to powers of 800 kV and underground routes with very short lines. The figure presents the typical generation profile of the different renewable technologies and cogeneration. DG technologies vary depending on the voltage level, so it has been assumed that in DG networks, high voltage, HV, 132 to 45 kV, the predominant generation is wind and cogeneration, medium voltage, MV, cogeneration, solar photovoltaic and mini hydro, and in low voltage, LV, solar photovoltaic. For the analysis, different typical profiles by technology have been used. The horizontal axis is in the hours of a typical day. The acronym SIN-GD stands for without distributed generation. On the horizontal axis are the identifiers of knots, on the vertical, the tension in P. U. The effect of active and reactive power injection on the high voltage network is shown in the figure. Reactive power has a greater impact on voltages than active power. The grid voltage increases, on average, by 0.16%/MW and 0.36%, were compared to the DG's active and reactive power injections. If DG was switched off at peak times, voltage values close to 95% of the nominal voltage would be obtained. The figure presents the variation in tension with different control strategies. The figure shows the voltage variation as a function of the degree of penetration at peak hours and outside peak hours. On the vertical axis, the voltage variation in the final node is presented, in the horizontal, the degree of penetration of DG, in percent divided by 100. The impact of DG penetration on the voltage profile of medium voltage networks depends on segmentation and the demand scenario. The impact of the DG in the peak period, or in the valley, connected to the final knot, has the tension of the same knot, with respect to the scenario without DG. The voltage increase is linearly proportional to the active injection of power into the node. The figure shows the voltage variation as a function of the degree of penetration at peak hours and outside peak hours. On the vertical axis, the voltage variation in the final node is presented, in the horizontal, the degree of penetration of DG, in percent divided by 100. The impact of DG penetration on the voltage profile of medium voltage networks depends on segmentation and the demand scenario. The impact of the DG in the peak period, or in the valley, connected to the final knot, has the tension of the same knot, with respect to the scenario without DG. The voltage increase is linearly proportional to the active injection of power into the node. Since DG is expected to occur in low voltage grids, LV, the most significant results of the impact of injection on all nodes of 50 kW and 50 kVAr are shown in the figure. In this it is observed that the impact on voltages differs according to the network analyzed. The rural air network has the greatest impact of active power on voltages, since the average Rx ratio is greater than 4. The low voltage network, LV, associated with the 630 kV underground line has the least voltage variation, because it is the network with the shortest average length of the lines. In this network, the impact of distributed reactive power is greater than that of active power, since all the nodes are very close to the CT and the voltage drop in it is more important than that which appears in the lines. The figure shows how the voltage of the different low voltage networks varies if the level of DG penetration increases, from 33% to twice the power of the net demand. The injection is homogeneous in all the knots of the network. There is a greater variation in tensions in aerial networks than in underground networks. Specifically, the 250 kV associated grid has the highest sensitivity to active power injection, as the grid is much longer than the rest. As it has higher impedances, the effect of the variation in power flows is also greater than in the rest of the networks. The figure shows the voltage variation depending on the location of the DG. The impact of the 50 kW injection has been analyzed. 3 locations of this injection have been studied, concentrated in an end-of-line node, distributed in 5 nodes that are end-of-line, and distribution of the injected power among all the nodes of the system. On the other hand, the more the active injection is distributed in the grid, the lower the impact on voltages and therefore the lower the probability of overvoltages. This is the situation that could be expected in the future, where different PV units are installed on a DG basis. Regarding voltage control strategies in the 50 kW distributed DG, the following voltage control possibilities are contemplated. Control with unit power factor, maximum reactive power generation capacity, power factor 0.95 capacitive, and maximum reactive power absorption capacity. Power factor 0.95 inductive. As shown in the figure, the injection of active energy into the grid significantly affects voltages. The impact is greater in rural networks than in urban ones, where the impact is very small. As can be seen from the grid associated with the 250 kV, operating with a unit power factor can cause local overtensions. Therefore, in most operating situations, reactive power absorption by the DG is necessary in order to be able to compensate the overtensions. If reactive power is absorbed at the DG connection knots, F, D, P, 0.95 inductive, these overvoltages can be partially corrected. The figure shows the voltage variation as a function of the voltage control strategy, in the case of underground urban networks. The type of DG technology, due to its optimal sizes due to economies of scale and current remuneration, fundamentally determines its size and location. For example, in distribution or medium voltage networks, the predominant DG is high power cogeneration or wind power plants located at specific points. In medium voltage networks, photovoltaic, small hydro and medium power cogeneration more distributed throughout this network, and in low voltage grids, solar photovoltaic generation of small nominal power is expected to predominate, which will be widely distributed throughout the network. The generation profile of each technology and its correspondence with demand determine the impact on voltages. Cogeneration plants, associated with production cycles, partially follow the hourly demand curve. Solar PV generation, with daytime production, adjusts to the demand curve in summer, although in winter it does not contribute during peak nighttime. It is difficult for the distributor to respond in real time, in medium and low voltage networks, to the variations produced by DG, since the last voltage control is carried out in the medium voltage substation park. DG should contribute to voltage control, as increasing penetration levels does not guarantee current and voltage quality. Smart distributed generation. Optimization of distributed generation capacity and voltage profile improvement. Distributed generation, DG, has been a challenge and an opportunity to develop various innovative technologies in power generation. The benefits of employing DG are evaluated using the Voltage Profile Improvement Index, VPII, and the line distributed generation, DG, has been a challenge and an opportunity to develop various innovative technologies in power generation. The benefits of employing DG are evaluated using the Voltage Profile Improvement Index, VPII, and the Line Loss Reduction Index, LLRI. The line voltage stability index is obtained with the Newton-Raphson method in the vicinity of the stress collapse point and, therefore, validates the importance of the proposed method. The optimal value of DG capacity is solved with the particle swarm optimization, PSO, methodology, thus maximizing the quality of power. The inline voltage stability index calculated using the PSO-based method accurately identifies critical lines. To assess and quantify the benefits of distributed generation, appropriate mathematical models should be used, along with distribution system models, and energy flow calculations to arrive at indices that measure the benefits. Among the many benefits, three main ones are considered: Voltage Profile Improvement Index, PI, Line Loss Reduction Index, LLRI, and Line Voltage Stability Index, LVSI. DG improves the voltage profile, VP, on various buses, and PI quantifies this improvement. Based on its definition, the following attributes are: if PI is less than 1, DG is not beneficial. If PI is equal to 1, DG is not beneficial, has no impact on the system voltage profile. If PI is greater than 1, DG has improved VP. In general, the highest value of PI implies the best location for installing DG in terms of improving VP. Another important benefit is the reduction of losses in power lines. By installing DG, line currents can be reduced, thus helping to improve LLRI. Based on its definition, the following attributes are: if LLRI is less than 1, DG reduced electrical line losses. If LLRI is equal to 1, DG has no impact on system line losses. If LLRI is greater than 1, DG has caused more electrical line losses. This index can be used to identify the best location to install DG. The minimum value of LLRI corresponds to the best DG location scenario in terms of line loss reduction. The important aspect of the stress stability assessment is to find the distance, measured in electrical units, to the maximum load point from the current operating point. LVSI is used to accurately obtain the proximity of the operating point to the voltage collapse point, by the index given by the equations of real power flow and reactive power flow, in terms of transmission line. The model aims to minimize the objective function designed to reduce power loss, and improve system performance, for various values of distributed generations. The study has been conducted on an IEEE 30 bus system. The diagram shows the standard IEEE 30 bus system. The buses having less voltage profile were identified after performing Newton-Raphson load flow analysis and are chosen as the locations for the DGs to be installed. Here the bus numbers 30, 26, 7 and 29 have less voltage profiles at the base case and hence were chosen as locations for DG installations. The selected cases were: Case 1, DG located at bus 30. Case 2, DG located at bus 26. Case 3, DG located at bus 7. Case 4, 50% of DG located at bus 30 and bus 26, and Case 5, 50% of DG located at bus 7 and bus 29. The increase in the Voltage Profile Improvement Index, PI, is evident after connecting DG, as shown in the tables. The voltage profile of the base case was calculated at 2.9441 pu. The best results were obtained when DG was connected for Case 1, for 0.2 pu, and for case 5, for 0.3 pu. In this case, the reduction in the line loss reduction index, LLRI, is evident after connecting DG, as shown in the tables. The LLRI estimates a maximum reduction of 30.93% in case 1, for a DG of 0.2 pu, and a reduction of 41.94%, for a DG of 0.3 pu, in case 4. The figure shows the variation of the improvement in the voltage profile, on bus 30, for different DG ratings. When the DG capacity was randomly generated between 0.05 pu to 0.5 pu, the values of the line stability index of the conventional load flow and the similar PSO-based method. Considering that the conventional method is based on exact mathematics, the differences may be due to the metaheuristic nature of PSO. The table shows the comparison of detection of critical lines. The effectiveness of the line stability index is also reflected in the correctness in the determination of critical lines under various load conditions above the base case for the IEEE 30 bus system. For different load conditions, up to a critical load of 273.942%, lines 7 and 13 were consistently the critical ones, according to the exact Newton-Raphson load flow method compared to the approximate PSO method. This validates the accuracy of the PSO method. The table shows the increase in the maximum load capacity of the system after connecting DGs on several buses. Conclusion: DG in a distribution system clearly show that can improve the voltage profile, reduce electrical line losses, improve voltage stability index, and enhanced utility system reliability. There are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.